Good evening, friends. Today I am going to explain about hardware support for preserving exception behavior. Here there is a concept known as speculation. This means that when an instruction is moved from one place to the other place, the proper exception property of that instruction should not be changed. We can achieve this strategy only if at the starting we'll predict the instruction which will cause an error or the instruction which is mispredicted. So there are four methods that have been investigated to support ambitious speculation without introducing erroneous behavior. So the first one is the hardware and OS cooperatively ignore exception. This is like when an exception, this property preserves the exception of the correct program, but ignores the one for the program which has some errors. So, but this property is, cannot be applied for all the programs. It might be unexpectable by some programs. Okay, so the next one is instruction that never raise exceptions are used. The one best way to ignore the instruction which introduce some erroneous behavior is we'll use the instructions which does not raise any exceptions. Okay, means the speculative instruction that never raise exceptions are used. And there is a thing called checks. The checks are introduced to determine when exceptions occur. Okay, whenever the exception occur, the checks are introduced. And the third one is poison bits. The set of status bits called poison bits are attached to the result registers returned by speculated instruction when instruction causes exceptions. When an instruction causes an exception, these poison bits are attached to the instruction which cause exceptions. Okay, the poison bits cause fault when normal instruction attempts to use the registers. Whenever we set a poison bit and if it is used by a normal instruction, when the normal instruction tries to use the registers, the poison bit causes a fault. Okay. The next one is hardware buffer the instruction till it is no longer speculative. Means there is a mechanism used to indicate that the instruction is speculative or not. Once it is found that the instruction is speculative, the hardware buffers instruction until it is certain that instruction is no longer speculative. Means the instruction is the hardware buffers the instruction until that instruction becomes no longer speculative. Okay, we need to distinguish between exceptions that indicate error and that would normally terminate. Means some constraints such as memory protection violation and some concept like page fault, we must be careful while distinguishing the exceptions. If a speculative instruction should not have been executed, handling the unneeded exception might have some negative performance effect. So, like if there are unnecessary instruction which are used in our code, and we must, and like by using those unnecessary instruction, it might cause some negative performance effect, and we might not get the proper output. Mean that it will be like incorrect execution of the program. And if you do such thing, it will be it will increase our cost of this exception may be high. Okay, so here note that instead of terminating some programs, we will be allowed to execute it even though the result will be incorrect. Now let us see a small piece of code. So here the given code is like, if a equal to 0, then a equal to b, else a equal to a plus 4. Here a is at the location offset of R3 and b is at a location offset of R2. So the code can be written as load the offset address of R3, that is nothing but A, will be loaded in register R1. Okay, next branch not equal to 0. Compare if the register R1 is equal to 0 or not. This R1 represents here, like a, you are checking here a equal to 0. Here this means if the instruction R1 is equal to 0 or not. Indirectly we can say if we are checking like a is equal to 0 or not. Okay, if it is not equal to 0, we are directly jumping to this label. This adds R1 equal to R1 plus 4. This instruction is nothing but a equal to a plus 4. So if it was not equal to 0, this instruction would have been executed. After, like if it was equal to 0, we'll load offset of R2 into the register R1. Okay, next we'll, after loading of the offset of R2 is nothing but instruction B, we will be loading it into the R1. After doing this, next step is to jump to the label L2. It is nothing but storing the, here we are storing the instruction A in the register R1. This is the general way of writing this small piece of code. But in terms of speculation, we can write our code like this. Here we are loading the instruction A in register R1. This offset of R3 is nothing but instruction A. Next, we use one more register. This is because this is the speculative load. Here we do this because if we were to load instruction B again in R1, and here it is already the instruction A is being loaded to R1, and if here it was R1 and we load instruction B here, the first value of R1 would have been changed. So here we use a temporary register R14. Okay, so here we loaded both A and B in two different registers. Here we check whether the instruction R1 is equal to 0. If it is equal to 0, we come to this instruction, and here it adds Here it has R1 plus 14 and stores it into 14. Sorry, R1 plus 4 and stores it into R14. If this wasn't the case here, if it was not equal to 0, then it would have come to the label L3. I'm sorry. If this was equal to 0, if it would have come to the label L3, and it would have stored the value of A in R14. If it was not equal to 0, it would have come to this instruction and adds R1 plus 4 and stores it into R14. So the result of these both will be stored in R14. Here we are using extra registers just to in order that this R1 won't this value will be preserved, and this B won't be again stored in R1 in order to preserve our value of A, which was stored in R1. In this case, it is not necessary to know whether instruction is speculative or not. This case is helpful only when a program is in error and receives terminating exception on a normal instruction. The next one which we are going to see is renaming will often be needed to prevent speculative instruction from destroying live values. Means we are going to rename the registers in order to preserve its value. Renaming is usually restricted to the register value. Because of this restriction, the target of stores cannot be destroyed and stores cannot be speculative. Here, whichever value we are going to be stored in here stores, this is known as stores, that won't be speculative. If we do the renaming, the values that is stored won't be changed and it will be speculative by the help of the following method. And like one more approach is that preserving the exception behavior when speculating introduce a speculative version of instruction that do not generate terminating exception, and instruction to check for such exceptions. Means there are some exceptions which do not cause a terminating exception. Means the exception will be continuous and do not terminate at some point. That time even this method will be useful. So here in this code, we are going to use speculative load and speculative check. Okay. R3 with offset of R3, that is nothing but value A, will be loaded into a register R1. Next, the offset of R2 will be loaded into R14. SLD is nothing but speculative load. This instruction causes no termination. Next, branch not equal to 0, R1. We are checking whether the instruction A is equal to 0 or not. If it is not equal to 0, then jump to this instruction. We will add R1 plus 4 and store it into R14. If this was equal to 0, then we would come here and offset of R2, that is nothing but instruction B, SPECCK, this means speculative check. This as I discussed above, this instruction checks whether there is any instruction which does not terminate at any point of time, and it helps to resolve. After this instruction, we come here, we'll directly jump to the label L2. The offset of R3, that is instruction A, will be stored in register R14. The third approach for preserving exception behavior tracks exception as they occur but postpones any exception until a value is actually used, preserving the occurrence of exception although not in a completely precise fashion. Means the until the actual exception occurs, the behavior is postponed, and this is not a clear completely precise fashion. If a speculative instruction uses a register with poison bit, the destination instruction does not have any effect. Whereas if a normal instruction attempts to use a register source with its poison bit turn on, the instruction uses the instruction causes a fault. In this way, any program that would have generated an exception still generates one. This means if a normal instruction tries to use a register source, that will cause some kind of poison bit will be turned on, and it won't allow us to use that register in order to preserve its value. Some poison bits occur only on register value and not on memory values. Stores are never speculative, thus trap if either operand is poison. This will this poison bit will occur only on the register values, means it will occur on these values, but it won't occur on this type of value. This is memory values and this is register values. In this code, we are loading the offset of R3 in the register R1. This is nothing but instruction A. And next is SLD R14 comma offset of R2. We are loading offset of R2 in instruction 14, which is nothing but instruction B. This is instruction A. SLD means speculative load. Branch equal to 0, check with the register R1. If this is equal to 0, then add R1 plus 4 and store it in R14. If it is equal to 0, then go to label 3. Store the offset of R3 in R14. If this was not equal to 0, then you would have come here, add R1 plus 4 and store it in R14. I hope you guys understand my concept. If you have any doubts, please comment. Thank you guys.